It's a pleasure to introduce this time Jesús Zavala. He did his PhD at UNAM in Mexico City University 2005, and then moved on to a postdoc at Waterloo, Toronto, CITA, 2005 through 2007 through 2010, and after that he had and is currently still at Waterloo at the Perimeter Institute, where he is having an associate postdoctoral researcher's position since 2011. So today you will tell us about dark matter physics and new clues from the dwarf galaxies, please.
Thank you for inviting me. It's a pleasure to be here. So yeah, I'm going to talk about an aspect of my current research, which is related to the possibility that dwarf galaxies might actually give us a clue about dark matter physics other than the gravity, of course. So this is just a brief outline of my talk. I'm going to discuss the current paradigm of dark matter, both when it comes to our understanding of how structures form, and also what are the assumptions made for this paradigm when it comes to the physics of microphysics of dark matter. Then I will talk about these challenges that I think are quite important nowadays, and that might be telling us something new about dark matter, and that in particular related to these two fields, which is warm dark matter and self-interacting dark matter, and then I will just conclude. So let me say, of course, that if we believe in the idea of two different observations in the last decades, we have gathered evidence that there is a new type of particle, which is the dark matter, that is actually 80% or so of the matter content in the universe should be dark. And what I want to emphasize here, instead of just give a list of this evidence, is just the importance for this hypothesis for our understanding of how structures form in the universe. So we can understand how the universe goes from a state that is very homogeneous, as is imprinted in the CMB, to the large-scale structure of the universe that we see today, and ultimately how, from large-scale structures, galaxies form. And this is, of course, the ultimate goal, to make this connection. So the hypothesis that the dark matter is a new particle gives us this framework of understanding, and it's actually quite successful. On the other hand, we might ask ourselves, maybe dark matter is not so dark, maybe the particle that makes the dark matter has other interactions other than gravity. And of course we have been looking for these interactions for a while now. Here's just a diagram illustrating these possibilities. So we might have dark matter actually being produced as it was perhaps in the early universe, directly from the interactions of standard model particles, for example, at the LHC. So we are looking for that. We might also look for the interactions of dark matter particles with standard matter particles in a laboratory on Earth. So the nuclei and the dark matter particle might collide, and that collision can be recorded, for example, in Italy. Here is the Xenon 100 experiment. And we might also look for the possibility of dark matter annihilating, for example, to create the standard model particles. And of course, here in the Oscar Klein Center, there are different people working on this possibility. This is the Fermi satellite, which is looking for gamma rays since 2008. And maybe some of these gamma rays are actually originated by the annihilation of dark matter. Now, do we have an actual clue of where to look for these kind of interactions? We don't know, of course, what's the theory that ultimately governs these interactions, but we might have a clue when it comes to the scale of those interactions by asking what's the abundance of dark matter. So if that scale of interaction is of the order of the weak scale, then we recover, or we obtain the right abundance of dark matter today. That is called the WIMP miracle, weakly interactive massive particles, and that's why people have been looking for this intensively in the last decade. So here, the point I want to make is that, of course, we are hoping for these signatures, and we are hoping to detect them soon by different experiments. So for example, in the case of annihilation, this is the cross-section for annihilation as a function of mass, and these are the current limits by the different, by the Fermi telescope looking at different objects, the galactic center, the dwarf galaxies, etc. And the point I want to make is that we are reaching this region where favor supersymmetric models that predict these WIMPs have this natural scale, which is the weak scale for interactions. And the same when it comes to the nuclei scattering, we are also reaching that scale. So this is again the cross-section, this time is the WIMP with nucleon cross-section as a function of mass. Here is, for example, the limit for xenon 100, other experiments. And again, we are reaching this scale where we are supposed to find these particles. Of course, in principle, this scale extends all the way down, but we are reaching at least the first, we are reaching this natural scale, and we might wonder, okay, until where are we willing to push this further if we don't find anything? So that's one of the points that I want to make. And the second important point I want to make is that these two hypotheses that are in the paradigm, the current paradigm of dark matter. So there is this dark matter hypothesis that dark matter exists. There is a new particle, and what are the properties of that particle? Well, it's assumed that dark matter is cold, so that means that early on in the universe, when the particles were moving relativistically, they were able to erase perturbations of certain scales just by moving from under-dense regions to over-dense regions. And that scale is related to the mass of the particle. The more massive the particle, the smaller the fluctuations they can erase before they become non-relativistic, and that they cannot move forward, move further and erase this perturbation. So this is a very well-known effect, and you can understand it or its effect if you make a plot of the density fluctuations as function of scale. You have, for example, the large scales that we can measure from the cosmic microwave background to the smaller scales, gravitational lensing and the Lyman alpha forests. And of course, the current model fits this very nicely, and that's a success of the model. But in principle, it doesn't tell us anything, or there is no observation beyond this point. What happens here? In principle, if SIDM, you see the cold dark matter paradigm is right, then this scale should go all the way down here, roughly 6 orders of magnitude. So from 10 to the 10 solar masses to 1 Earth mass. In mass, the scale of the fluctuations that can collapse. And then is where we would expect a cutoff according to this idea that dark matter should be WIMPs. But how cold really is dark matter is ultimately given by observations. And what does that mean? Why, when people call dark matter cold, what do they mean? So here's, if you extrapolate the velocity dispersion of those particles till today, well, you have this redshifting effect. And then today, these dark matter particles will be moving at this speed, which is roughly the fastest speed of a snail. So the point that I want to make here is where do we draw this line depends on observations. And today, this line is more or less at this point, 10 to the 10 or so solar masses. That corresponds to a velocity of 0.04 kilometers per second, roughly the speed of a car. So here is where we are now. We cannot really rule out warmer kind of dark matter particles today because observations tell us that that's still a possibility. So in principle, the model would work equally well until what we know now, if the mass of the particle would be of the order of 1 or 2 kiloelectron volts. The second point, the second hypothesis is that it's traditionally assumed that dark matter is collisionless. That means it doesn't collide with itself. And one of the most elegant evidence of that is the bullet cluster. So you have seen this picture for sure before. This is a picture of the collision of two clusters. Here the X-ray image can be seen in white, yellow, red, blue. And the clusters are colliding with themselves. And as they collide, they produce these shocks and these interactions that are clearly related to how gas interacts between itself. And the weak lensing measurements are given in green, so that gives a measurement of the mass distribution. And that, of course, creates this large offset between where the visible matter is and where the dark matter is. And that's evidence of the existence of dark matter, but it's also evidence that dark matter should be collisionless, at least much less collisional than the gas. That's the other point that I want to emphasize. This doesn't mean that dark matter has to be collisionless all the way. It just gives a restriction, an upper limit on the collision and cross-section, which is roughly given here. This is the cross-section for collision divided by mass, per unit mass. This is of the order of 1 centimeter square per gram. So that's where the current limits are. So I wanted to emphasize these 2 points because they will be clear in later on in my talk. But before moving on, I wanted to show this video, which is going to be hard to see with the lights.
Let me see.
But let me. Yeah, there you can see a little bit better. So how do we study structure formation in the universe is through the use of n-body simulations. We start with the CMB initial conditions. We give us an initial condition statistically how the universe was early on, and then we just create perturbations or take those small perturbations as initial conditions, and we put them in a computer and just evolve them. This is just gravity, so there is no gas there. It's essentially just the dark matter particles interacting. And as gravity continues and moves, clumps things together, well, you form these structures, which are called dark matter halos once they virialize and become self-bound structures. And 2 things I want to emphasize here. Of course, you need large supercomputers to do this. This is a simulation from 2008 called within the Aquarius project. And one thing you might notice immediately is the large abundance of structures there. So there are very small halos of dark matter that are self-bound and that they are meshing together to create this larger structure. So you have these 2 predictions of the models that will be clear later on. One is this very large abundance of structures, and the second one is the high density that you have here. The particles are, the colors represent the density and coldness of the particles. So the structures that are colder and denser have this white color. So you see how you have a structure in the center that is very dense, and also each of these is very dense, and of course you have this very large abundance of structure. So this is a Milky Way size halo. So this is how, in this model, a halo like the one our own Milky Way leaves should look like, according to the model. Now, of course, from going to these kind of simulations to the actual observations that we did today, and to how actually galaxies are in reality, of course, there is a very long process. Here we stop in the simulations. There's just initial conditions, and then we create this dark matter halo. It's very beautiful, very simple physics in principle. It's just gravity. And then, of course, becomes extremely complicated from then on. You have different effects, cooling, all the physics of gas, star formation, and feedback that we don't fully understand. Just wanted to emphasize that we are trying to understand the properties of dark matter by looking at these galaxies at the end. So of course, it's very important to know that this is there, and that this has to be dealt with somehow. That's why dwarf galaxies are perhaps the best way to try to understand if there is additional physics for dark matter, because dwarf galaxies are extremely dark matter dominated. So in principle, many of the processes that are here are diminished or are less important, and perhaps then we can understand or get some better idea if there is something new going on. So let me talk about these challenges that I think are quite interesting, and that are really, really in the last years have become, they are all challenges actually, but they have been renewed through new observations and through new analysis, and I think now they have become quite an important challenge for the model. So let me talk about this. So again, you have one of these simulations, you have your dark matter simulation, and then the simple thing you can do with them is simply just count the number of cell-bound objects that you have. That's one of the simplest things you can do. So here you can see you have 1 halo, 2 halos, etc., and then you just make a plot of the number of these halos as a function of mass. Just to count them and then compare if that's something reasonable compared to the number of galaxies that we see as a function of mass as well. Of course, as I was saying before, to do that you have to understand galaxy formation at least to a certain extent, because there is a process that modifies the scaling between dark matter halo mass and a stellar mass, for example, for a galaxy. Without going into details, here's a plot of the number density per unit mass as a function of stellar mass. So the points are observations of galaxies taken by the SDSS survey, and the green and red are predictions from the model based on this simulation once you include a galaxy formation model, the standard one. I'm not going to go into details. The point I want to make is that the match is quite nice, very nice actually, until this scale, which is the dwarf scale. Here there are some problems, so we shouldn't believe here the observations below this, they are incomplete. But this model tells us that we maybe understand galaxy formation at this level, and that the model matches the observations very well until those scales. Now, this is a work that I did back in 2009. You can do the same now, but instead of looking at stellar mass, you look at something similar, which is the rotational velocity of the galaxy. So this time, you look at the gas in the galaxy and see how fast that galaxy is rotating by looking at the H1 gas. And again, this is the abundance of galaxies as a function of that rotational velocity. In this case, the rotational velocity is of course a better proxy of the halo mass, right? Because it doesn't depend on how stars form, it just gives an idea of the gravitational potential. So all I want to emphasize with this plot is that here's the same scale that was put there, so that's the scale of dwarf galaxies. And again, these are the predictions of the model, and here roughly they match the model reasonably okay. But from this scale to smaller scales, there is a huge discrepancy between the model and observations. And that's something that has to be understood. Yeah, this is not fully understood with current benchmark galaxy formation models. So the same models that work here, apparently they don't work here. So that's one of the first issues. In other words, what I'm trying to say is that perhaps the model is predicting too much of these small halos flying around that apparently shouldn't be there. There are possible solutions, and I'm not going to discuss them further, but at the end, even if we manage to solve this problem, I want to emphasize this: if the model is right, there must be a vast amount of these substructures or structures floating around that simply don't form galaxies and we don't see them. That's a clear prediction of the model. So the second prediction of the model is that dark matter is very dense in the center. So here is again a picture of one of these Milky Way halo structures, and if you go to exactly, for example, you go to one of these substructures or you go to the center, you just assume of one of them, and you ask yourself just very simply, what's the density profile? You take spheres around the center, and then you just go towards the center and see how the density grows with radius. And this is what you find. So the density essentially diverges towards zero, with a slope that is very close to 1. So that's another prediction, very clear prediction of the model. And again, we can ask ourselves, okay, is this consistent with observations? And the answer seems to be tricky when it comes to dwarf galaxies again. So again, let me remind you, this is a dwarf galaxy, so it would be, by eyes, it's hard to see, right? This is a collection of stars. It's a galaxy, it's cell-bound, it has a large dark matter halo. We know there is dark matter there because the dynamics of the stars there are simply not explained by the luminosity of the stars. But you see that there are not many stars there. This is another example. So there are really systems that are dominated by dark matter, so the gravitational potential should be dominated by dark matter. So it's a problem that was recently brought forward, which is related to the density of these dwarfs. So you can take one of these dwarfs and just simply ask, what's the enclosed mass within certain radius? You can take the dynamics of the stars and do that with high degree of certainty, I would say. And this is what is shown here. The points are just simply the enclosed mass of the circular velocity within a certain radius for these 9 dwarfs of the Milky Way. In green, red, blue, and gray are the predictions for the model, for substructures or for halos that should be the places where these galaxies live. And what the problem here is that there is this population of subhalos that is just too dense and too massive to be consistent with any of those. And that's of course something that has been, this was brought forward in 2011, 2012, and so far there is no clear explanation of why this is so. You can go a little bit further, although of course it becomes more uncertain, and ask actually what's the slope of the profile, how the mass is changing with radius as I showed before. Without again going into details, you can do it for two different galaxies. This is for sculpture and fornax. You can make a slope, and what you find is that this idea of I was showing before here, this prediction of having something very close to 1 is disfavored by the data here, where in this case the cost would be something that diverges towards the center, so this would be the blue line, is disfavored by the data, so the data seems to prefer something, halos that are flatter in the center, so the density is constant in the center. And that's of course very hard to obtain in cold dark matter. Now, just for completeness, let me tell you how people have been trying to solve this within the model. So of course, as I said before, galaxy formation is very complex. So one of the possibilities is that you have star formation and then supernova feedback, and that feedback creates a gas blowout, so similar to AGN feedback, which is for supernova, and then you drive the gas outwards, and by doing so, you decrease the density of dark matter in the center. So this has been shown with simulations, and it's an understood process that is understood, but it doesn't seem to work at the scale of dwarfs. So this is again the halo mass. This is the slope of the density profile within 500 parsecs, essentially just the slope at a given radius. And this is for massive galaxies, and these are the galaxies like the Milky Way satellites. This is the green points are the simulation without the supernova feedback, and the crosses with supernova feedback. So you see how the feedback creates these cores, expands the dark matter profile, and makes them look more like a core. On the other hand, for smaller masses, that doesn't seem to be so. So you simply don't have enough energy in these galaxies to create these cores. And something similar can be said about this other problem that I discussed briefly, this too big to fail problem, which is the one related to this issue. And again, here, without going into that plot, the possibility is simply that if the halo of the Milky Way is less massive than 10 to the 12, you might solve the problem. But then you run into other problems, which is, for example, the two most massive satellites in the Milky Way wouldn't be bound to the Milky Way. So what I'm trying to say is that these two problems are very hard to solve within SIDM, and they may actually be telling us something that goes beyond the standard dark matter physics. So that's what I want to move on now, and I want to talk about these possibilities. So one is, I talk how dark matter may actually not be cold, but it could be warm. So this is something I did back in 2009. This is again one of these simulations, dark matter simulations within CDM and warm dark matter. It's very hard to see in the contrast the difference, but essentially if you pay more or less attention here in the voids, you see more structure here than here. That of course can be quantified. Here, just to remind you, the difference was this cutoff in the power spectrum. So you form less and less structures below that scale. And that will of course solve this abundance problem that I was talking about. This is what we shown in 2009. You can forget, behind this line is just problems with the simulations. But above this line, again, here are the observations and the predictions of CDM, which have this large discrepancy, and then the predictions of warm dark matter with 1 kiloelectron volt. And you see, of course, that the match is perfect, essentially because you naturally, by introducing this cutoff in the power spectrum or in the structures that can form, you can actually explain these observations very nicely. Of course, I want to emphasize that warm dark matter is a solution, but only if it's really, really close to the current constraints. If the constraints get better by just a bit, and there is no cutoff in the power spectrum, then it wouldn't work. It would essentially mean that you will need the same kind of Qs that you need for cold dark matter. And what about the distribution of dark matter in the center? So again, this is this issue. This is cold dark matter, warm dark matter, and you can see immediately that you produce less of structures, and also the structures that you produce are less dense. You can see it here in this plot. This is the circular velocity profile or enclosed mass as a function of radius. The same plot that you saw before, the dwarf galaxies. And then once you do it in warm dark matter, you reduce the density and you get more consistent with the data. Now, can you create cores in warm dark matter halos? That's a big issue. You cannot, at least not as big. This is a nice way to see it is to the phase space density, the coarse grain phase space density. You can estimate this coarse grain phase space density early on in the universe, and that depends on the mass of the particle. And then you can relate that coarse grain phase space density. I mean, there is a theorem that tells you that that phase space density can only decrease in time. And then you can find the size of the core. And long story short is that for the kind of masses that are allowed today, you essentially end up with cores that are too small to explain the observed cores that need to be larger than 500 or 600 parsecs or so. So warm dark matter doesn't seem to work in that way, but this is an important point, and that's one of the things I want to work on. No one really has shown this. This is just an estimate based on this kind of scaling laws, but no one has shown it with a simulation, because these simulations are quite challenging. Now, to end my talk, I want to dedicate more time at talking about this other possibility, which I think is quite exciting, which is the idea that dark matter can actually collide with itself. And here the idea is quite simple. So you relax this hypothesis of having collisionless dark matter, and then you allow for the possibility for richer physics at the scale of the microphysics of dark matter. This idea was originally introduced over a decade ago. In this case, it was just like a hard sphere kind of interaction, so it essentially just the area or the effective area of interaction gives you the cross-section for your interaction. Here is again cross-section divided by mass. But of course, in principle, you can have, or maybe I would even say that it's more natural to think that the cross-section might actually depend on the velocity of the particle. And that has two advantages. One is that I was talking about this cluster constraint, so like the bullet cluster, right? You have a constraint there that is very strong, or reasonably strong, but it's at the scale of the clusters, where the velocities or the typical velocities between the dark matter particles are quite high, of the order of 1,000 kilometers per second or so. But nothing tells you, nothing stops you from thinking that at the scale of dwarfs, 10 kilometers per second or so, you can actually have a cross-section which is much higher. So dark matter behaves collisional at the scale of dwarfs, and maybe these observations are telling us that. And it behaves essentially collisionless at the scale of clusters. And of course, these kind of ideas are not just, although the kind of studies that have been done so far is simply just a phenomenological model, but they are actually motivated by particle physics. So for example, this is a paper by Waterloo and Viner of 2011. Here the idea is to introduce a new force that acts between the dark matter particles, and only between the dark matter particles. This is called, for example, the Sommerfeld enhancement when it comes to electron and positron annihilation, and of course in dark matter annihilation is something that was quite fashionable. It is still some years ago. Because you introduce this new force, then you enhance the cross-section. Like for example, you would think naturally, for example, the Coulomb interaction is an example of that, right? And then you would get an enhancement that depends on the velocity. So that gives you this scaling that I have plotted here. Of course, in this way, you avoid the constraints, and at the same time, you can have a strong effect here. So we took these kind of models, and we put them into a simulation. So again, we have the gravitational interactions, and on top of them, we add a probabilistic approach for the possibility that dark matter can collide with itself. In this case, given by the cross-section per unit mass, the relative velocity of the particles, the local density, and the time step in the simulation. So we introduce these into the simulations, and this is one of the results that we get. So this is again the standard picture, a Milky Way halo with all its substructures. And actually you can see that in simulations, halos are triaxial, so they are not spherical. Once you introduce collisions, the collisions tend to isotropize the orbits, so you get something more spherical. You reduce the number of substructures because some of these substructures get evaporated because of the collisions. You inject a kinetic energy to the surrounding material, you inject some of the kinetic energy into these substructures, and then they simply evaporate. and they are also less dense, as I will show in a second. And you can understand this essentially very simply just by looking at this formula and see how many collisions you have in the history of the universe, and you will see that you just need a few in the center to create the desired effect. So that's a way to tune your model, that's a way to fix the cross-section. And this is what you get. So this is one of our strongest contributions to this particular field. So here is again the same problems that I was talking about, the enclosed mass as a function of radius. Here are the observations. This is the SIDM picture. It doesn't work, it's just too dense. Once you include the collisions, you start reducing the density in the center of these structures, and then you get to the level that the observations require. The same with the density profile. You start with something which is very, very dense. You continue with the collisions until you create a core, which is of the order of the cores that are observed in the dwarf galaxies. Furthermore, you can ask yourself, okay, of all these models that you had here in the beginning, which ones are more preferred? These ones that have a constant cross-section, or these ones that have a velocity dependence. And that of course, tells you something more. It's telling you an extra level of detail about the physics of dark matter. And what we found is that if the cross-section is constant, the range where this works is very small, just too small. So I would say our results favor the idea of this velocity-dependent cross-section. But this is of course not a strong claim, because there is still this window where things can work. So finally, I want to also make this point. When you allow for the possibility of collisions, you also change the predictions for the direct detection experiments. So the direct detection experiments for dark matter are looking for the scattering of nuclei of dark matter, and they require, or they have an input there, which is what's the local distribution of dark matter. Of course, nobody knows, no one knows at the scale of the solar system where is the local distribution of dark matter. What all these models assume is that this distribution should be as in SIDM, because that's the preferred model. So what we show here is, well, this is just another way of seeing, this is just the phase space structure of these two types of models. So SIDM again have all this, here you can see nicely the substructures highlighted there, and self-interacting has less substructures. And this is the velocity distribution. So SIDM is hard to see there, but if you follow the blue or the green, that's SIDM there. And once you include the collisions, as I was saying before, you essentially, what happens in a collisional gas, right? So you get something that gets Maxwell-Boltzmann type of distribution. So you get something similar to this. So the point to make is that perhaps if dark matter is not the standard SIDM particle, then you should also take this into account, and that affects the direct detection experiments. So it's a small effect, but it's still an important effect. So that's something we also found recently. So let me conclude with the following. I think these are very challenging times and very exciting times for the standard picture that we have of the dark matter model. This standard picture, what I mean by that is the SIDM model that of course is very, very successful, and I'm not saying that we should abandon it. Simply that it is challenging for these two reasons. So we have the SIDM coupled but with WIMPs, of course it could be action, it could be something else. Then we have these two problems, I think, that should be solved, or should be tried to solve in the following 5 years or so. Which is, one is of course the experiments are reaching this expected level for the WIMPs to be found. If we don't find them in 5 years, then I think that's a problem. And the second is these problems with the dwarf galaxies, which I think is quite exciting, quite important. So we have to understand why we are seeing this overabundance of halos in the simulation that we simply don't see in reality. And the second is, of course, the densities of these satellites are simply inconsistent with what the theory is telling us. Of course, it might be that all of this is telling us something which is clear, which is we don't have a full understanding of how galaxies form, and maybe the solution is there. But as I was trying to convince you here, I think that's quite difficult, especially when it comes to the second problem. But it might also be that it's more exciting than that. It might be that dwarf galaxies are actually telling us something about dark matter physics. So they might be telling us that dark matter is warm. They might be telling us that dark matter is collisional. So just to end, this is the last slide. So what do I want to go there in the next years or so is to actually go around and try to convince people that it's a good time to actually start looking into these alternatives more seriously. What I mean by that is to actually put gas physics on them. So as I said before, even in dwarf galaxies, the gas physics shouldn't be as relevant as it is, for example, in Milky Way size objects. It is still relevant, and we need to understand at what level affects the predictions of the different models, and essentially put them at the same level as SIDM, right? And that means treating them in this way, and try to find how galaxies form and evolve in these type of systems, and then compare them both, all of the possibilities, and see which one is more closely related to what we actually see. Okay, so with that, we're finished. Thank you.
Thank you very much. Very interesting talk. Questions, please. Yes, please.
So, in SIDM, the missing knowledge problem has gone a long way to be solved by selection effects and starch suppression through ionization.
Yeah.
If you include that in WDM models and self-interacting models, do you get like a problem?
Yeah, so that might be, right? So that's exactly what I mean by this. No one has done it, or they are starting to doing it right now to include these effects in world dark matter cosmology, right? But one has to say, right, that there is a degeneracy here, because you say, okay, I solved the problem with feedback and star formation and reionization and all that. Then if I put warm dark matter, I'm going to solve it as well. It's just going to be require less feedback, less of all this stuff, right? So you have to.
It's a different fine-tuning.
Yes, it's a different kind of issue. But the thing is, let's try to put the physics in all of them and see what all of them predict, and try to use as much observations as we can to favor one model over the other.
Yeah, just really quick second question.
Sure.
For the too big of a cell problem.
Yes.
So I guess the normal idea is that the densities of the core tail of the density are shallow or more shallow, so they get disrupted easier.
Yes.
Has actually been shown to give a deficit between like 30 and 40 kilometers per second in these simulations, or is that?
No, I mean, what you mean is that perhaps these subhalos will be disrupted?
Yeah, well, in other words, does the does easier model solve, or has it been shown to solve it?
It's just that you have so the physics of tidal disruption is in the simulations, right? Because the physics of the gravity and the tidal field is completely and fully included in the simulations. What is not is the effect of gas physics, right? The gas physics can create cores, and then your substructure that is going to fall into the halo is going to be less dense, and because it's less dense, the tidal torques are going to act differently.
Well, I know simulations have been done in concepts of CDM, but they've been trying to get cores in order for it to be disrupted.
Yes.
But you already have cores.
Yes.
So I was wondering if that naturally happens with WDM.
It should, but no one has checked this. Yeah, but it should.
Other questions, please? Yes, Lars?
Is there any way to check just the shape of galaxy halos by weak lensing, microlensing, or something like that?
Yes, but not at the level of where you would see a discrepancy. So of course, for scales for galaxies as small as this, it's just not possible. You can do it for ellipticals, or you can do it for clusters, but then you don't reach really the inner parts where there is an issue with the model, right? So warm dark matter and self-interacting dark matter would be essentially the same at larger scales.
Laura?
Yes, I have a question also in this direction. So in your case of this interacting dark matter, would you expect a signal somewhere else than just in the
Yes.
box in some sense?
Yeah, so for example, in the early universe, well, let me make a comment first about warm dark matter. So warm dark matter will have a different history of how structures form, because they form later. So that will have, for example, an effect on high redshift galaxies, or even the population of first stars, because the first stars are supposed to form in these dark matter halos and then collapse to form the first population of stars. That wouldn't happen in the same way in warm dark matter. Now, self-interacting dark matter, the thing is that the collisions are so few that it might have a minor impact at high redshifts, but at lower redshifts, it might change, for example, the orbits of the satellites. So that would be another way to look at it. It might have different kind of effects when you actually form the. So this is a big galaxy, right? This is like a Milky Way type of galaxy. But because it changes the distribution, the angular momentum of the dark matter particles in the center, even in the center, this thing forms in the center. And although you cannot resolve the very inner center, you do affect, well, it's hard to see there, but you do affect the inner 1 kiloparsec or so. So the inner parts of a galaxy like the Milky Way and the galactic bar, for example, is formed in the central parts of the galaxy. So that might have an impact. I just don't know what it is. That might be a way to find other ways to test this model.
Yes, please.
You said that for self-interactive dark matter, the distribution is more isotropic for dark matter. Is it also true for the satellite galaxies?
Yes.
So there has been this recent paper by Nordita showing that part of the Andromeda dwarfs are in the plane.
Yeah.
Is that correct?
Yeah, I think that's a very, I'm familiar with that problem. I mean, it's not only the Andromeda galaxy, it's also the satellites in the Milky Way show this kind of, all of them seem to be aligned in a plane. And that's something that is not going to be solved with this. It's more, I think it's much more complicated than that, because to have this kind of coherence in the way these satellites fell, that's quite challenging. Here, structure forms in a very similar way as SIDM. So you would have filaments, where you have these structures falling in and also coming from different directions. So overall you would get with collisional dark matter, for example, you would get something that is isotropically distributed. Also the subhalo effect. So you would not get this kind of structures. So that's a different problem.
I had just two questions. One, well, the plots that you show where you put the observed satellite galaxies on, how come no one puts the LMC and the SMC on those plots? Because those are more massive.
But the thing is that they are much more massive.
So
let me just go here. So these would be 60, they would be somewhere here.
So the too big to fail thing is that there's nothing, it's the absence of things in between the LMC and the SMC and the observed classical dwarf galaxies.
Yes, yeah, I should have emphasized this. Yeah, so you have two very massive galaxies, and those are relatively okay, although CDM is, I have to say, if the mass, and that's some of the points I want to emphasize, so if the mass of the Milky Way is lower than we currently think it is, then you might solve this problem. But then you will not get massive satellites as the Magellanic Clouds. So it really is what I was saying, that there's a missing link or something between those two. Yeah, so there you have this population, and then you have the others there, and there is nothing in between.
And the other question was just more of a comment that there's been recent work by Katherine Johnston and Larry Woodrow and others looking at the tidal disruption of the Sagittarius dwarf, and by looking at how the leading and trailing tidal streams precess in the Milky Way's potential, there's indications of significant triaxiality in the Milky Way's dark matter halo. And I was wondering if that observation of triaxiality put a constraint on these self-interacting dark matter models.
That would be very interesting to check. I mean, it all depends on the level of where it does, right? I mean, to my knowledge, the strongest constraints are from the ellipticity of cluster halos. And that's really, really the strongest. But I would be interested to check if these are actually stronger somehow.
So the main difference between self-interacting dark matter and warm dark matter at small scales, what is the main difference that you could distinguish observationally?
The strongest difference that I would point out is that in one dark matter you wouldn't get cores, or you would get cores that are very, very small. So you will have to, but you get things that are less dense. So here would be something in the density plot. It would be something like this one, but less dense. So well, like this. So you might solve this issue, but if the galaxies really have cores, which is something that I want to emphasize, is not completely settled. But if they do have cores, then one dark matter doesn't work. So that's the main difference. And of course, the history of formation is different. So as I was saying before, one dark matter halos would collapse later on than self-interacting dark matter halos, for example.
And the evidence for cores is, you think it's too weak?
It's strong in larger galaxies. So galaxies that are, let's say, in between this and our Milky Way. But those galaxies, because they are in a different regime, then you can blame the core on galaxy formation processes. Now, the evidence for cores in dwarf galaxies is tentative at this point, I would say. You only really have these two cases. So you need better data, and more than better, really more complete, because you only get an incomplete information from the dwarfs. You just get the velocity of the stars along the line of sight, and their two-dimensional position. But to reconstruct the gravitational potential, you would need the six-dimensional, right, phase space, and then you could get it all. So you would need proper motions of the stars, and we don't have that. Once we have that, then we can be more, this can be more convincing.
And what's the main weakness of self-interacting dark matter?
Well, I don't know if that's a weakness, but I would say that some people would think that you are just adding another degree of freedom by letting these things collide. So you are adding a cross-section. So some people don't like that. They try to stay with the simplest models. But I wouldn't say that's a weakness really, because we don't know what the dark matter particles are. So it's fair game, I think.
So I have a related question.
Please,
Since we have this sort of narrow window for it does depend on velocity. I mean, in sort of more natural units, what does this correspond to? Can you sort of make models where this is natural sort of gauge interaction strength or something like that, or?
Roughly, so this actually corresponds to the neutron-neutron strong interaction cross-section.
It's really strong.
Yes, but this is again, so for these models to work, you would need a whole hidden sector dark matter with their own interaction, so it doesn't, those new interactions between dark matter particles, they don't connect with the standard model particles. So you would need some kind of model that works in that way. But people have come up with these models, and not only that, they have come up with how you produce dark matter in that way, if it's consistent with the correct abundance. All of that is solved, or you know, there are proposals. That's what I mean.
Do these self-interacting dark matter models, do they have implications for direct detection? I mean, I think there were some models in which the dark matter might not even penetrate the atmosphere.
Yes, exactly. So there you will need, again, you will need to separate, right? So when I was putting this plot, okay, you can have these interactions between the dark matter particles, but in principle, the cross-section should not be related, or again, I'm not a particle physicist, but it should not be related to the cross-section for scattering with nuclei. So you would have a strong interaction between the dark matter particles, but you could have weak interaction between the dark matter particles and the nuclei. And then by having both, you can look at the detectors. But if the interactions were strong, you are right, they could.
But that would be observationally allowed, right? I mean, or just to, I mean.
It would be, yes.
If the dark matter never penetrated the atmosphere, then it wouldn't get down to the mines, and it would be consistent with the non-observation.
Absolutely, yeah. That's true.
Okay, any other questions? If that's not the case, then let's thank Jesús again. That concludes the lectures for today.